Hello everyone and welcome back to another video. Today we're going to be talking about inequalities. So before we get started, we're going to take a look at an example where we're going to look at some sort of linear equation and then be able to look at a number of solutions that we can figure out using an inequality. So the first question says, suppose you received a $20 gift card for iTunes. Each song costs $1 and today any album costs $5 with taxes included. What are all of the different combinations of songs and albums that you can buy if you spend all of your $20? So what we're going to do first is we're going to create a little table here. So starting off with our songs, and then we're also going to have all of our albums here. So starting off with buying just albums, if we buy 4 albums, we're going to be able to buy 0 songs because 4 times 5 gives us $20, and we don't have any money left over for any songs. If we buy 3 albums, then we have money left to buy 5 songs. And we can continue down this table having 2 albums and 10 songs, or 1 album and 15 songs, or we could spend all of our money on songs and get no albums. Now in the second part, we're going to let S represent the number of songs and A is the number of albums purchased. We're going to need to write a linear equation in 2 variables to model this situation. So thinking about what we have here, whatever we're buying has to equal to a total of $20. If we're looking at the number of songs that we can buy, we are spending $1 per song. So 1S is going to be our first term. And we're going to add the number of albums that we purchase at $5 per album. So we have the number of songs that we purchase at a rate of $1 each, plus however many albums we buy at a rate of $5 each, has to give us a total of $20. Now in this next part, we see how valuable inequalities are going to be when we're asked to list all of the possible combinations of songs and albums that we can buy for less than or equal to $20. So starting off again with our table of values, we could have our songs and albums. And we can start off this process by saying, okay, we could have 4 albums and 0 songs. We could have 3 albums and 0 songs. We could also have 3 albums and 1 song. We could have 3 albums and 2 songs, 3 albums and 3 songs. And all of these combinations are going to be less than or equal to $20. So you can see here that the number of combinations is quite a lot. If we were to continue this table, we could go all the way up until 20 songs. And 0 albums. And we have a number of combinations that, again, is a little tedious to list out. So this is where having an inequality is really helpful. So in order to create a linear inequality, we're going to look at our original linear equation, and we need to figure out which inequality we're going to use. So just as a reminder here, let's go ahead and talk about all of the different inequality signs. We could have this one here. We could have this one. We could have this one, or we could have this one. So once again, reading from left to right, let's say, for example, if I say 1 is less than 3, that is true. I could have 1 is less than or equal to 3. I could have something like this, where 4 is greater than 2, or 4 is greater than or equal to 2. And all of these are true statements. So what we're trying to do is we're figuring out, well, which inequality sign are we going to use, what's going to be on the left-hand side, and what's going to be on the right-hand side to make it a true statement. So for us, we're going to take exactly what we had before, $1 per song plus $5 per album has to be less than or equal to $20. So when we think about it like that and turn our applications into some sort of sentence that makes sense to us, writing out a linear inequality is really not that bad. So what we're going to have to do now is we're going to draw a graph that represents the possible combinations of songs and albums that we can purchase for less than or equal to $20. So again, depending on which variable we'd like to consider as our X or Y, your graph is going to look a little bit different. We're either going to have one that looks kind of like this, and again, this is a really rough drawing there, or we could have one that looks like this. And I'll show you what we end up with in a second. So for us, if we have 1S plus 5a, let's go ahead and write that down again. 1s plus 5a is less than or equal to 20. Let's go ahead and turn the s and a into x and y for a little bit of an easier time. So here we'll say that s is equal to our y. So we'll have 1y, or just y, plus 5x is less than or equal to 20. And from here, what we can do is we can actually come up with a graph where we're going to subtract 5x from both sides. So let's subtract 5x here. And we'll end up with a linear inequality where we have y is less than or equal to negative 5x plus 20. And this allows us to graph our equation on this grid here. So let's go ahead and start off with our y-intercept. So knowing from our slope-intercept form, y is equal to mx plus b, our slope is going to be negative 5. That's our m value. And our y-intercept is going to be our b value. So our y-intercept in this case is going to be 20. So let's go ahead and put that on the graph. So we're going to start off at 20. Let's do this in red. And we can see because of the slope, negative 5 is the same thing as negative 5 over 1. So we're going to go 5 down for every 1 unit we move to the right. So we're going to go 5 down, 1 to the right, 5 down, 1 to the right. And we keep doing that until we reach the end here. So 5 down, 1 to the right, and 5 down, 1 to the right. Now what we're going to do here is we're going to connect all of our points here with a straight line. And maybe I'll change this to red. So once I get this line down, we'll do that. And let's make it nice and red. And then I'll just reiterate my points right here. So we had 1, 2, 3, 4, and 5 points there. So before we do anything else, let's consider what we have just done. And maybe what I'll do is I'll label this. So we said that our x values were going to be the number of albums that we have purchased. Let's go ahead and do that, number of albums. And for our y values, we said number of songs. So if we were looking here and we were trying to interpret our points that we plotted, here we are saying that if we buy 4 albums, we're going to have 0 songs. If we buy 3 albums, we have 5 songs. 2 albums, we get 10 songs, and so on. So this matches up with the chart that we had at the beginning of our question here. And now what we're trying to do is we're trying to figure out, well, what are all of the different possible combinations of songs that make sense? Well, if I were to pick a random point here, let's say, for example, I decided to choose something like this. So this point at 2, 2 means that I have 2 albums and 2 songs. So 2 albums, 2 songs. So that's going to be $10 from albums and $2 from songs. So 10 plus 2 is 12. That would make sense because that's going to be less than $20. So that would be a potentially valid solution. So what we're going to have to do is we need to figure out what this is going to look like mathematically. So essentially what we can do is we can pick any test point, okay, that's underneath or above this line that makes sense for us. So for us, we can go ahead and do this. We can choose that as our test point. And we have to make sure that this is mathematically valid. So let's go ahead and plug these values into our original equation. So we said that we had 1s plus 5a is less than or equal to 20. So we're going to use our test point. So we said our test point was 2, 2. So $1 for every song that we buy, and we're getting 2 songs, and $5 for every album that we purchase. Oh, that was going to be 2 for our test point, has to be less than or equal to 20. So once again, 1 times 2 is 2, 5 times 2 is 10, and that's less than or equal to 20. So 12 is less than or equal to 20, so that is true. So this means that we have to shade the region below the line. Now let's say, for example, we decide to pick a point that was somewhere way out here, which really, again, just by looking at this graph and trying to figure things out, it really wouldn't make a lot of sense. So let's pick, for example, let's say we decide to buy 10 songs, or 10 albums rather. We don't have the money to buy 10 albums. So if I were to plug this in algebraically, 1s, so 1 times 0 plus, and this point here would be 10, 0. So 1 times 0 plus 5 times 10 is less than or equal to 20. We can see here that we're going to have 0 plus 50 is less than or equal to 20. So we know that's not true. So we would not be shading in this region anyways. So again, choosing that test point can make your life a little bit easier if you decide to use one that you already have an idea of whether or not it's going to be correct. So since we know that we're going to shade this in, we're going to add kind of a caveat here. So really we could pick any of these points ideally. So any of these points on our graph could be a solution, but just to make things a little bit easier, we're going to just shade this entire thing in. And notice what's going to happen here is I'm only going to shade in all of my solutions in quadrant number 1. So for those of you who remember all of the different quadrants, if I were to sketch this out, we have quadrant 1, 2, 3, and 4 here. And the reason why we kind of restrict our values to just quadrant number 1 is if I decided to choose a point, let's say, for example, out here where we have -1 albums and 0 songs, well, we can't really purchase -1 albums. So that would not be part of our solution set. But realistically, anything that is shaded in this green triangle could be a potential option as long as those are all whole numbers. So what I mean by that is, let's say we decide to choose 0, 0. That would work because that means that we're buying 0 albums and 0 songs. What wouldn't work quite as nicely is, let's say, for example, I decide to buy 1.5 albums. That wouldn't work because obviously we already know that you can't buy half of an album. So all of our solutions would actually have to be any of what we call our lattice points. So anything where there's an intersection of grid lines, and all of these are really our solutions. So any of these points here that I am placing on the graph would realistically be our solutions. So again, just to reiterate, only lattice points in quadrant 1 are solutions. So again, just in summary here, we can see how having an inequality helps us figure out all of the different combinations of solutions rather than having to write them down one by one. So here on this page, we're going to look at some inequalities with just one variable. And these are ones that you have already done back in junior high. So these should be pretty quick for us. So what we're going to try to do is we're going to try to isolate for x on one side. It doesn't really matter which side we are on. The only thing we have to keep in mind is if you divide or multiply an inequality with a negative number, you need to flip the sign. So I'll show you what I mean in just a second here. So 3 minus 2x is greater than, or rather less than 19. So let's go ahead and do this without flipping the sign. So what I'm going to do first is we can add 2x to both sides. So plus 2x. And we'll have 3 is less than 2x plus 19. I'm going to subtract 19 from both sides. So minus 19 from the left and the right. And we're left with negative 16 is less than 2x. And finally, to get x by itself, I'm going to divide both sides by 2. So what this leaves me with is that negative 8 is less than x. Or I could flip this around and I could say that x is greater than negative 8. So for our solution, we would draw a number line here. And let's say, for example, we have negative 8 right here. Since we do not include negative 8 because it's not greater than or equal to, so in this case, we don't include negative 8 here. So it's greater than negative 8. So we're going to go ahead and put an empty circle there at negative 8. And we're going to move on towards the right because we know that our solutions are everything greater than negative 8, but it does not include negative 8. So now to demonstrate what happens if you do end up flipping the sign, or when do you need to flip the sign, let's go ahead and do the question again. Except now in this case, I'm going to subtract 3 from both sides. And that leaves me with negative 2x is less than 16. If I divide both sides by negative 2, if I do not flip the sign, look at what happens. If I don't flip the sign, I'll end up with x is less than negative 8, which is not true. So we need to make sure that whenever we multiply or divide by a negative number in an inequality, we need to flip the sign. So we're going to go ahead and flip the sign and have it be x is greater than -8. So if you're confused about why we have to flip the negatives in an inequality when multiplying or dividing by a negative number, we can look at a quick little example here where 20 is greater than 10. If we multiply both sides by -1, we would end up with -20 is greater than -10, which we know is not true. So here in this case, we're going to have to flip this sign to maintain that inequality. So essentially what you can think of it as is if we are flipping the signs of the terms or numbers on both sides of an inequality, basically we're going to have to flip our inequality sign to maintain that same balance. Looking at our second example here, we already have x on the left-hand side, so we'll just subtract 7 from both sides, and we'll have 5x is less than or equal to -20, and then dividing by 5 on both sides leaves us with x is less than or equal to -4. So if we were to draw our number line here, we have -4. Because we're now working with something that is less than or equal to, we can see that for us, we're going to draw a circle at -4, and we're going to also fill it in because we're including that value of -4, and all of our solutions are less than or equal to -4. So we can see that that's going to be our solution set. So again, just to recap, if we have open circles that look like this, we're either working with this inequality sign or this one. If we have a closed circle, we're looking at this one with the equal sign underneath for less than or greater than. So now we're going to apply these same ideas of open circles and solid circles to graphing, and we're going to look at linear inequalities in two variables. So in these two equations, ax plus by is less than c and ax plus by is greater than c, we can see that there's no equal to here. So we can state that the boundary line must therefore be dotted. And then that really is just represented by having a line that would look like this instead of a solid line, which in this case for ax plus by is less than or equal to c, and ax plus by is greater than or equal to c. We can see that we have those two inequality signs. In this case, the boundary line must be solid. So instead of having those dotted lines, we're just going to have a solid line just like so. So note that the ordered pair xy is a solution if it satisfies the inequality. So basically what we're going to want, so we want a true statement. So we want a true statement for this to satisfy the inequality. And we're going to have certain regions called our solution region or solution set. And these will contain all the points that satisfy an inequality. So we're going to shade in whatever region is true. So I know this is a lot of information to take in. So let's go ahead and work through a few examples to see how we can apply these ideas. The first part here asks us to algebraically determine if -2, 5 is part of the solution set to the inequality 2x plus 3y plus 24 is less than or equal to 0. So starting us off, we know that we have an ordered pair, so this means that we have an x and we have a y value. And the only thing that we need to consider is this part up here in the green that says an ordered pair is a solution if it satisfies the inequality. So what we're going to do is substitute in our values of x and y into this inequality, and we're going to check to see if it's true or false, because we do want a true statement if it is a solution, and we're going to end up with a false statement if it is not part of the solution set. So we can say that we have 2 times -2, 2 times -2 plus 3 times 5 plus 24 is less than or equal to 0. Okay, let's see if that's true. -4 plus 15 plus 24 is less than or equal to 0. -4 plus 15 is 11. 11 plus 24 is 35. And we know that that is not less than or equal to 0. So we can say that this is false. And then therefore, -2, 5 is not part of the solution set. So being able to prove if something is or isn't part of the solution set is pretty straightforward. If we know that we have our ordered pair and we're given an inequality, all we're going to have to do is plug in that ordered pair and check to see if that statement is true or false. Now in this next question, we're going to graph the inequality 5x minus 2y is less than or equal to 10 without a calculator. So our first step is to convert to slope-intercept form. Convert to slope-intercept form. And if you recall from Math 10c, we know that slope-intercept form is y is equal to mx plus b. We know that we're working with a linear equation with two variables. We don't have a quadratic here. So if we have a y, we have an x, we can always convert this into slope-intercept form. And what this will allow me to do is find out my y-intercept, find out my slope, and we can graph it on here without using our calculator. So starting us off, we have 5x. Let's make that a little bit neater. 5x minus 2y is less than or equal to 10. We can subtract 5x from both sides, so minus 5x minus 5x. I have negative 2y is less than or equal to negative 5x plus 10. So we can see that mx plus b taking shape here. And then dividing both sides by negative 2. So I'm going to divide the entire thing by negative 2. That leaves me with a positive y on the left-hand side. Now remember what we said earlier about flipping the sign. If we're dividing by a negative number, we're going to flip that inequality sign. So I'm going to flip it this way. So now we have y is greater than or equal to. And then from here, we have negative 5x divided by 2. So negative divided by negative gives me a positive. So 5 over 2x. And now we have 10 divided by negative 2 gives me minus 5. So now that we've converted this to slope-intercept form, or really what we've done is we've converted one side to slope-intercept form, we still have our inequality here. What we can do is we can use y is equal to 5 over 2x minus 5. We're going to use this to graph. Use this equation to graph our line. So before we graph the line, we're going to take another look at our inequality sign here. So we have something that is greater than or equal to, which means that we're going to have a solid line rather than a dotted line. So looking at our equation, we have 5 over 2x minus 5. We have a y-intercept of negative 5. So I'm going to start there. And using my slope of 5 over 2 means we're going to go up 5 units and then go 2 to the right. We're going to go up 5 and then 2 to the right. And we run out of room on this side. We can come back the other way. We're going to go 5 down and 2 to the left over here. So having those points plotted down means I can now connect those with a solid line once again. So having a solid line, let's go ahead and put that down. And I'll go over those points again just so we can see them clearly. So we get something that looks like this. So now what we're going to have to do is use a test point to determine our solution set. So before we get started, the thing that I caution students about is we cannot choose a test point on the line. So here we go. Don't choose a test point on the line, because if I have an inequality sign that is this or this, means that the point is not a solution. And then if we have a sign that looks like this, then that means that our test point is part of the solution. So we don't want to choose a point that we already know is or isn't going to be part of that solution set. So we're going to choose something that is off the line completely. So for us, a really easy test point to use, let's use 0, 0. So our test point is 0, 0. And what we're going to do is plug that into our inequality here. We can use either the one that we have started off with, or we can use the one that we've converted. Typically, we do want to use the one that we have started off with, because we know for sure that's what's given to us in case we have done the math incorrectly. So we have 5 times 0 minus 2 times 0 is less than or equal to 10. So we can see that we have 0 minus 0 is less than or equal to 10. So 0 is less than or equal to 10. That is true. So 0, 0 is part of the solution set. And what we're going to do is we would shade in everything that is above the line here. So all of these are solutions. And once again, just to reiterate what I meant in this blue section here, we don't want to choose a test point on the line because we already know it's going to be part of the solution set. So if I were to use this point as an example, let's say we used 0, -4. If I were to plug this into my inequality, we have 5 times 0 minus 2 times -4 is less than or equal to 10. We know that we're going to have 0 plus 8 is less than or equal to 10. We already know that's going to be part of that solution set. So you want to test everything either above that line or everything below the line. And once again, let's say, for example, we decided to choose a point that was below the line. Let's say we have, let's choose this one here. Let's go with 4, 0. So if I decide to use 4, 0, and maybe I'll do this in a green because that'll be easier to see. So 4, 0. If this was the point that we chose, you would have 5 times 4 minus 2 times 0 is less than or equal to 10. We're going to have 20 minus 0 is less than or equal to 10. We can already see that this is false. So this is false. So what happens in this case? Well, if we can see that the point that we've chosen results in a false statement, then we do not shade the region containing 4, 0. So if we don't shade in this bottom region, well, that just means that we just shade in the top region instead, or the other region instead. So this makes it a lot easier to understand. It doesn't matter if you choose one that's technically in the correct region, because if it's false, well, you just shade in the region that you didn't choose a point from. Now on this page, we're going to look at how to shade in the solution set without using a test point. And the key to this is writing the inequality in slope-intercept form. So once again, just to reiterate, slope-intercept form is y is equal to mx plus b. Even if we have an inequality sign here instead of an equal sign, it's still going to be the same thing. So essentially what we're saying is if the inequality is greater than or equal to, we're going to shade above the boundary line. So for this one right here, we would look at something like this: y is greater than or y is greater than or equal to. Now, if the inequality is shaded less than or equal to, we're going to be looking at going below the boundary line. So for this case, we're going to look at something like this: y is less than or y is less than or equal to. So essentially, if you have your y on the left-hand side, that makes things a lot easier because it tells you whether or not you're shading above or below the boundary line. Now, the only caveat to that is if you happen to have everything on the flip side. So let's say, for example, you have something that looks like this and you have some sort of equation on the left-hand side or some sort of expression, something is less than y. Basically, what we're looking at in this case is really the same thing here. So if your inequality sign opens up towards y, you're going to be shading above that boundary line. So here we're going to look at a few examples where we graph and figure out our solution set. So remember, our job here is to isolate for y and put this into slope-intercept form. So in order to do so, let's subtract 6x from both sides first. We'll end up with 3y is greater than or equal to -6x plus 15. And then we'll divide both sides by 3. So divide the entire thing by 3. And we'll end up with y is greater than or equal to -2x plus 5. So before we actually start graphing this, we're going to take note of our inequality sign. So since it's a greater than or equal to, this means that we're going to be looking at a solid boundary line. So because we have this sign right here, we're looking at a solid boundary line. So keeping that in mind, we're going to start graphing our inequality. So we have -2x plus 5. So that means we have a y-intercept at +5, and a slope of -2 means we're going to move down 2 and then go 1 to the right. So we're going to keep doing that until we reach the end of the graph. And I can just go the opposite direction from here. So I'm going to go up 2 and 1 to the left. And then I can connect these all with a straight line. So again, because we have a solid boundary line, I don't have to worry about using a dotted line. Let's go ahead and make that green. And we'll connect all of our points here. So now that we have that line down, we know that we're working with y is greater than or equal to. We're going to be shading everything above the boundary line. So we're going to shade above boundary line. So it's going to be everything above the line here. All of these are going to be part of the solution set. Again, we can verify this algebraically as well. Let's say, for example, I decide to use the point 30. So we can see that's firmly in the solution set. So we can use a test point just to verify. So if we have 30, we're going to plug this into my original. So 6 times 3 plus 3 times 0 is greater than or equal to 15. We'll have 18 plus 0 is greater than or equal to 15. So this definitely is the correct solution set. One thing to keep in mind here is that your points on the boundary line are part of your solution set, so just make sure you keep that in mind. Here you can pause the video and try out the second problem on your own. Here in these two problems, we're going to work backwards, starting with our graph of an inequality, and we're going to figure out the inequality itself. So to start us off, we're going to choose 2 points that can help us figure out the equation of the line. So we're going to choose 2 points that are relatively easy to work with. Let's use this one right here, our y-intercept and our x-intercept. So we're going to have 8, 0, and we'll have 0, -4 as our 2 points. So what we're going to do is we're going to label these as x1, y1, x2, y2. And again, it doesn't really matter what your order is for these 2 points. I could switch around the x1, y1, and x2, y2. Again, it's just personal preference here. And what we're going to do is we're going to use our slope formula. So we know that we have m is equal to y2 minus y1 over x2 minus x1. So plugging in our values here, we'll have -4 minus 0 divided by 0 minus 8. So this gives me -4 over -8, which reduces to give me 1/2. So from here, we see that our slope is 1/2. So our m value is 1/2. The only thing that's left for us to do is to figure out the b value. And we can see pretty quickly here that your b value is equal to -4. So putting this back into slope-intercept form, we have y is equal to 1/2 x minus 4. And looking at our inequality here, we have a dotted line, and we're shading below the dotted line. So let's go ahead and write this down. So we have a dotted line shaded below, which means that we're going to be looking at this inequality where y is less than. So essentially, we're going to just replace this equal sign with this less than sign. So we have y is less than 1/2 x minus 4. So once again, we can always verify with a test point. And in this case, let's choose something that is not in the solution zone. So we have 0, 0 is probably the easiest one to work with. So let's use 0, 0 as our test point. So we'll have 0 is less than 1/2 times 0 minus 4. And this leaves me with 0 is less than -4. So this is false. So that means that the solution set is the other region. So essentially what we've done here is we've chosen a test point in this region. So we are potentially seeing if we're shading this all in, but the test point that we chose made the inequality false, which means that this is not shaded in, which means that therefore the other region, all of this stuff down below, is shaded in. So we know we've done this properly. And this gives us our inequality of y is less than 1/2 x minus 4. Here you can pause the video and try out the second question on your own, and then unpause to check your work. Now let's look at an example where we'll have to create an inequality and then graph it to determine the solution set. Here it says that we have a sports equipment manager makes footballs and soccer balls. One football required 4 minutes on the cutting machine, and then the soccer ball requires 3 minutes on the machine. So our first step is to determine an inequality that represents the number of each type of ball that can be made in 60 minutes or less. So let's define our variables. So here we have x equal to the number of footballs that are made. And then meanwhile, on the other hand, y is going to be equal to the number of soccer balls that are made. So our inequality here is going to be centered around making these soccer balls and footballs in 60 minutes or less. So really, we are saying that it has to be less than or equal to 60. And the left-hand side of our inequality then, we have less than or equal to 60. We are looking at 4 minutes per football. So 4 minutes per football plus 3 minutes per soccer ball have to be less than or equal to 60. And that gives us our inequality that we can work with. So for this particular question, we'll just go ahead and turn this back into an equation. So we have 4x plus 3y is equal to 60. And using this equation, we can just find our x and y intercepts, which give us 2 points that we can plot on the graph and then just simply draw a line through those 2 points. So to find the x-intercept, basically we're making y is equal to 0. So we have 4x plus 3 times 0 is equal to 60. That means we have 4x is equal to 60, and therefore x is equal to 15. So we have a point at 15, 0. So let's go ahead and plot that first point. So we're at 15, 0. And then for our second point that we can use, we know that our y-intercept is when x is equal to 0. So that means we have 4 times 0 plus 3y is equal to 60. So we have 0 plus 3y is equal to 60. And then dividing both sides by 3 gives us y is equal to 20. So that means I have a point at 0, 20. So let's go ahead and plot that up here. So again, just to help us keep things straight, we're going to label the bottom, our x axis, as the number of footballs made, and our y-axis as the number of soccer balls made. So before we actually draw our line, we're going to go ahead and confirm what type of line we're going to draw. We can see that in this case, we're looking at something with a solid line. So because we have that equal to sign, this is going to be a solid boundary line. So now we can go ahead and connect those 2 points here with a solid line. Let's do this in red. So we'll connect those 2 points. And now what we're going to do is we're going to select one point in our solution region to verify the graph. So in order to figure out which region we're going to shade in, we're just going to pick a point here that we can use as our test point. So let's say we use a test point of 0, 0, because that's the easiest point to work with. We have 4 times 0. We're going to plug this back into our original inequality. 4 times 0 plus 3 times 0 has to be less than or equal to 60. So that means we have 0 is less than or equal to 60. So that's true. So we want to shade the region with 0, 0 as our answer. Now, the only thing we have to keep in mind is that our solutions have to be in quadrant number 1, which means that we're just only going to shade in everything in this section here. We're going to avoid coming all the way down here. Now, the reason why, again, very similarly to one of the problems on the previous page, is that we can't have a negative number of football or soccer balls being made. So all of our solutions have to be kept in quadrant number 1. Now, what we can do is we can choose a point in our solution region to verify our graph. So let's use 2, 2. So we can see 2, 2 is going to be right here. And let's test this out. We have 4 times 2 plus 3 times 2 is less than or equal to 60. So we're saying that we're making 2 of those footballs. So 2 footballs takes 8 minutes, and 2 soccer balls takes 6 minutes. and this means that we have 14 is less than or equal to 60. That is true. And then the last thing here on this question is to state the domain and the range for this situation. So starting off with our domain, we know that we're talking about our x values, so we can state that we have x such that the smallest number of footballs that can be made has to be 0, and the greatest number of footballs that can be made is 15. So we have x is greater than 0, it can also equal to 0, and it can also equal to 15. And in this case, we can't put x is an element of the real number system because we can't have any decimals or fractions of footballs. So we're going to say that x has to be part of the whole number system. Similarly, with the range, we're looking for the lowest number of soccer balls that can be made. So in this case, 0. And the highest number of soccer balls we can see is 20. So it can equal to 0 and it can equal to 20. And once again, we're only looking at whole numbers for our soccer balls. For this problem here, you can pause the video, try it out, and then unpause to check your work. Here we're going to switch gears a little bit and look at quadratic inequalities in one variable. So really what this whole section is looking at is we are looking for x values. So looking for x values that satisfy the inequality. And the inequality will depend on the sign that's being used. So really this section here with these first two, we're looking, and you can see that the common denominator is this greater than or equal to sign. We're looking to see where the graph is above the x-axis. And for these two here, where we are looking at where it is less than 0 or less than or equal to 0, for these two, we're really looking to see where the graph is below the x-axis. So I know this seems a little bit complicated at first, but again, once we work through a few different examples, it becomes a little bit easier to work with. So in example number 1, we are being asked to solve x squared plus 16 is less than or equal to 10x. So our first step is to just isolate everything on one side. So we're going to subtract 10x from both sides. And we're left with x squared plus or minus 10x plus 16. Plus 16 is less than or equal to 0. So essentially what this is saying is what values of x will the parabola be under the x-axis or negative. So now in order to do this, we're going to look at the graph itself. So let's say we were to graph y is equal to x squared minus 10x plus 16. And we know through factoring that we can actually factor this out as x minus 8 and x minus 2, which means that we have x-intercepts at 8, 0 and 2, 0. We can go ahead and plot these 2 points down. So we're going to be at 8, 0 and 2, 0. And we need one more point. We need to figure out where the vertex of our parabola is. So again, we know that the midpoint of our parabola is going to be in between our two x-intercepts. So between 2 and 8, our midpoint here is going to be at 5. So when x is equal to 5, we can figure out what our y value is. So we have y is equal to 5 squared minus 10 times 5 plus 16. This means we get a y value of -9. So our vertex then is at 5, -9. So let's go ahead and plot that right down here. So 5, -9. And we can see that our y-intercept is going to be at 16. We can't really see it on this graph here. But let's go ahead and sketch a quick graph of our parabola. So it's going to look something like this. So again, you don't have to be super precise for this since we are only looking at our x values, and our graph is going to continue up just like that. So now to answer our question, what values of x will our parabola be negative? So we can see pretty clearly here that our parabola is negative in between these 2 points. All of this down here is our negative portion of our parabola. So what values of x will satisfy this inequality? Well, really all it is we're looking for all the points between 2 and 8. So everything in between 2, so x has to be greater than 2 and less than 8. And because of our original inequality, so we can see here our original inequality is less than or equal to, we are also going to include those points that are on the x-axis as well. So our solution is that x is greater than 2 or equal to 2 and less than or equal to +8. So now we're going to take a look at how to solve this algebraically. So there's actually 2 methods that we can do this algebraically. The first is using roots and test points, and the second method really is using roots and sign analysis. So again, it depends on what method your own teacher will teach you and which one you prefer as a student as well. So starting us off with our original inequality, we had x squared plus 16 is less than or equal to 10x. We're subtracting 10x from both sides, so minus 10x minus 10x. And our goal here is just to replicate a quadratic equation rather. So x squared minus 10x plus 16 is less than or equal to 0. So we can see that if we were to convert this into a quadratic equation, we have x squared we'll have x squared minus 10x plus 16 is equal to 0. And we're going to go ahead and factor this as x minus 2x minus 8 is equal to 0. So we can see that our 2 solutions once again are equal to 2 and +8. So you can see that what we've done here isn't really all that different to what we've done up here graphically, but the biggest difference is what we're going to do with these 2 points. So with those 2 roots that we just found, we're now going to create a number line, and I'm going to put my points down here. So from smallest number to your largest, let's put a 2 here and an 8. And what this has done is it's created 3 different intervals for us to look at. So here on the left-hand side, we're looking at everything where x is less than 2. In the middle here, we're creating a section where we have everything between 2 and 8. And then here on the right-hand side, we're looking for everything that is greater than 8. Since we're looking at something that can equal to those points, let's go ahead and underline all of our inequality signs. And we're looking to choose some test points within each section here. So next what we're going to do is we're going to choose a test point for each section. So our test point for this first section, where x is less than or equal to 2, let's choose x is equal to 0. So all we're going to do with that x is equal to 0 is plug that into the original inequality, or we can use the one that we have come up with to see if it is true or false. So this means that we have 0 squared minus 10 times 0 plus 16 is less than or equal to 0. So we have 0 minus 0 plus 16. 16 is less than or equal to 0. This is false. So that means that this interval is not part of the solution set. So you can say not part, or we can say this interval of x is less than or equal to 2 is not part of the solution. And now we're going to do the same thing with our middle section here. So we're going to choose a value of x between 2 and 8. So let's choose something right in the middle. Let's go with, let's say 4. So if x is equal to 4, and now we're going to plug it in to this inequality here. So we have 4 squared minus 10 times 4 plus 16 is less than or equal to 0. So this means we have 16 minus 40 plus 16 is less than or equal to 0. This gives me, what do we have? Negative 8 is less than or equal to 0. So that is true. So that means that the interval of x is greater than or equal to 2 and less than or equal to 8 is part of the solution. And now finally, let's take a look at the right-hand side interval. Let's choose a point where it's going to be greater than or equal to 8. So let's choose x is equal to 10. So we have 10 squared minus 10 times 10 plus 16 is less than or equal to 0. So we get 100 minus 100 plus 16 is less than or equal to 0. So we get 16 is less than or equal to 0. And again, because it's false, it's not part of the solution. So therefore, we can state that our answer or our solution is going to be x has to be greater than or equal to 2, but less than or equal to 8. So for those of you who are curious about sign analysis, we can just label that here as method number 3. And it's really more or less the same thing, except we're just going to be using plus or minus signs. So we'll start off here with our inequality here that we have x squared minus 10x plus 16 is less than or equal to 0. So x squared minus 10x plus 16 is less than or equal to 0. We already know that we could factor this as x minus 2, x minus 8. So we could potentially just show it like that. Now what's going to happen with this is we're going to create a table and we're going to have our different factors as our columns up top. So we'll have x minus 2 as my first factor, and we'll have x minus 8 as my second factor here. And in this last column, we're going to see if it is positive or negative. In this first column, what we're going to do is we're going to look for our test points. The test points that we choose is going to be dependent, again, on those intervals that we've set. So again, we've got 2 and 8 here. We have x is less than or equal to 2. Then we've got everything in the middle. X is between 2 and positive 8, including those values. And our third interval where x is greater than or equal to 8. So maybe what I'll do is I'll add one more column here. Let's do this. Let's have our intervals. And then we'll have our test points somewhere over here. So our test points. So our intervals, we said we have x is less than or equal to 2. And then we had x is in between 2 and 8. And then finally, when x is greater than or equal to 8. So let's pick some test points. So a point where x is less than or equal to 2, let's pick 0. So if x is equal to 0, all I'm going to do now is I'm going to plug this 0 into my factors. So 0 minus 2 gives me negative 2, which is a negative number. 0 minus 8 gives me a negative number. Since I'm multiplying these two factors together to give me the original here, negative times a negative, means we are looking at a positive region of the graph. Now, again, just to remind you what that would look like, we're looking at that interval of x is less than or equal to 2. We can see that it's definitely true. Everything that is less than or equal to negative 2, or positive 2 rather, is going to be a positive y value. We can take a look down here at our second interval, and let's pick a point in between. So let's go x is equal to 3. 3 minus 2 is a positive number. 3 minus 8 is a negative number. If I go a positive times negative, that gives me negative. And then now doing the same thing down here, we're going to choose a point where x is greater than or equal to 8. So let's go with 9. 9 minus 2 gives me 7, which is positive. 9 minus 8 gives me a positive number, and a positive times a positive gives me a positive product. So originally what we were looking for is we're looking to see when is this inequality negative, because we're looking to see when it's less than or equal to 0, and the only one that's going to be negative is that middle interval. So we can see here that this interval is the only part where it's negative. So again, your solution set here is going to be, so your solution is when x is between 2 and positive 8. So like I said earlier, it's just really up to you to decide which method you want to use, whether you're using test points and you're trying to figure out if it's true or false, or if you're going to set this up as sign analysis. Some people like this better. Some people like the test points better. Personally, I do like the test points better, but this is also something that you'll be learning in calculus as well when you're doing curve sketching without a calculator. Here on this page, you can pause the video, try out the questions on your own, and then unpause to check your work once you're done. So remember that you can always double check your solution by graphing your equation on a graphing calculator and just making sure that the portion of your graph that is supposed to be negative or positive does match up with your answer set. So sometimes you're going to end up with quadratic functions that don't factor very nicely, so we can just go ahead and use the quadratic formula. Here you can pause the video and then try this out on your own and then double check your work after you're done. Here in this next example, we're going to create an inequality in a real life situation. So we have a tennis ball being thrown upwards at an initial speed of 15 meters per second, and the height of the ball in h meters after t seconds is given by the equation h of t is equal to 15t minus 5t squared. So we're trying to figure out, first of all, the time period for which the ball is higher than 10 meters. So it's not higher than or equal to, so we can see that for the right-hand side of our equation, we're going to have something is greater than 10. So our height has to be greater than 10, but our height here is represented by this equation. So we have 15t minus 5t squared has to be greater than 10. So rearranging everything here, let's subtract 10 from both sides. We'll end up with negative 5t squared plus 15t minus 10 is greater than 0. From here, let's come up with our quadratic equation where we'll have negative 5t squared plus 15t minus 10 is equal to 0. And what we're going to do here is we're going to have our a, b, and c's. So our a value is 15, or sorry, rather negative 5. So a is equal to negative 5, b is equal to 15, and c is equal to negative 10. So when you plug everything into our quadratic formula, I'll skip ahead a few steps here, we will end up with negative 15 plus or minus the square root of 25 divided by negative 10. And we'll end up with two values, x is equal to 1, and we'll get x is equal to 2. Now, of course, you didn't have to necessarily use a quadratic formula for this one. For some people, it might be faster to do it just by using decomposition, or you can just divide everything by a -5 and factor from there. So because I'm running out of room, let's go ahead and open this up on a new page. So we said that we have our roots of x is equal to 1 and 2. So let's go ahead and draw our number line. We'll have a 1 here, we'll have a 2 here. And again, looking at our different intervals, we'll have x is less than 1, we'll have x is between 1 and 2, and x is greater than 2. We aren't including those points because of our original inequality where it does not equal 2, so we're not underlining those inequality signs. We're going to pick a few points that fit within our intervals. So here, let's say x is equal to, not 2, let's go with x is equal to 0. Over here, we'll go x is equal to 1.5, so 1.5, and over here we'll go x is equal to 3. So let's test out all three of these points here. So our original inequality said that we had -5t squared plus 15t minus 10 has to be greater than 0. So we'll plug all of these values into this inequality. So -5 times 0 squared plus 15 times 0 minus 10 is greater than 0. So this gives me 0 plus 0 minus 10. And we know that this is false. Looking at our middle interval here, we'll have -5 times 1.5 squared. Then we'll have plus 15 times 1.5. Then minus 10 is greater than 0. And from here, we'll get 1.25 is greater than 0. So this is true. So this will be part of our solution. And finally, for this last question, or this last interval, we'll have -5 times 3 squared plus 15 times 3. And then we'll have minus 10 is greater than 0. So this will give me 9 times -5 is -45. -45 plus 45 minus 10, that gives me -10 is greater than 0. And this is false, which means that our solution set is where x is in between 1 and 2. So going back to our original equation, the time period for which the ball is higher than 10 meters, we can say the ball is higher than 10 meters when t is between 1 and 2 seconds. For this next section, where we're looking for the time interval when the tennis ball is in flight, here basically we're saying when it's greater than 0. As long as that tennis ball is off of the ground, h has to be greater than 0. So in this case, our inequality is going to look like this. 15t minus 5t squared is greater than 0. Let's rearrange this a little bit. So we'll have -5t squared plus 15t is greater than 0. Let's factor out a -5t from both terms. So we'll end up with 1, or rather just a t, and then we'll have -3 is greater than 0. So we can see here that we have t has to be, and if we were to convert this, let's go ahead and do this. If we were to convert this into a quadratic equation, -5t then times t minus 3 is equal to 0, we will have two solutions. T is equal to 0 and t is equal to +3. And so again, on our number line, we would just go ahead, we'd have a 0 here, we'd have a 3. I'll let you pick your test points here, but really just for us, we're going to see that the interval where the ball is in flight is when t is between 0 and 3 seconds. So for this next question, you can try it out on your own. I'm just going to write the answer down just due to some time constraints, but really this is more or less going to be the exact same thing, except in this one, you probably want to use the quadratic formula because you have some coefficients with decimals, so I'd recommend using the quadratic formula here. So here, when we're looking at quadratic inequalities in two variables, this one won't really be too difficult now that we've done linear inequalities in 1 and 2 variables. The only difference is now we're working with parabolas instead of straight lines. So our first question here asks us to graph the quadratic function y is equal to x squared plus 4x plus 1. So we're going to need to do a little bit of work here since we don't have this in vertex form. So let's use the vertex formula to help us figure this out. So x is equal to negative b over 2a. We know that a is equal to 1, b is equal to 4, and c is equal to 1. So from here we get negative 4 over 2 times 1. That gives me negative 4 over 2. So that means that my vertex has an x value of negative 2. We're going to plug this back into this equation here. So we have y is equal to negative 2 squared plus 4 times negative 2, and then plus 1. So we get y is equal to positive 4 minus 8 plus 1. And we get a final answer of negative 4 plus 1, which is negative 3. So my vertex is going to be at negative 2, negative 3. So let's go ahead and plot that on our graph. So negative 2, negative 3. Let's look for some other points that can help us out here. Let's look for our y-intercept. We know our y-intercept is going to be at positive 1. So we've got our y-intercept right here at positive 1. We can see that it's 2 units away from our vertex. So crossing over that axis of symmetry means that we're going to go 2 units away from here. And we're going to get another point on our graph there. I'm not too worried about where our x-intercepts are going to be because we're really looking for everything that's going to be above the parabola or everything that's going to be below the parabola. But if you are curious and you decide to use the quadratic formula, we get x-intercepts of negative 0.3 and negative 3.7. So negative 3.7 is roughly about here, and negative 0.3 is probably about here. So again, we're not too worried about this. But the part that we do need to worry about is the fact that your parabola is now going to be that boundary line. So kind of like how we did linear equations earlier on, where that straight line was our boundary line, we need to figure out if this is a dotted line or a solid line. So we can see here that they're asking us for this particular inequality sign where y is greater than x squared plus 4x plus 1. So because we don't have an equal to sign, we're going to draw our parabola with a dotted line. So the boundary line is dotted. So let's go ahead and do a quick little sketch here. It looks something like this. Again, we're not too concerned about being accurate for this particular question because we're really just looking for where we are shading. So now let's go ahead and shade in the area that represents this inequality right here. So we're asking for all the y values that will be above the parabola that has been graphed. So really we're just looking at all of these here. We are not including the points on the boundary line because those are not part of our solution set. So now we're being asked if the origin is in the shaded region. If I did a better job of shading earlier, we would see that we just barely miss out on having the origin as part of our shaded region because we know that the point 0, 1 is going to be our y-intercept. So we know that our parabola is not going to quite intercept at the origin. So we can test 0, 0. So using 0, 0 as a test point, we have 0 is greater than 0 squared plus 4 times 0 plus 1. So is 0 greater than 1? That is false. So the area with 0, 0 is not actually part of the test, part of the solution set. So we know that we have shaded in the correct region. Now, if we were to do the opposite here and we wanted to go where y is less than all of this, we would really just shade in the rest of this graph and get rid of this shaded purple part instead. So now we have a whole bunch of expressions here and inequalities that we'll just summarize really quickly. So to summarize this whole section here, basically we're saying if we have y is greater than or y is greater than or equal to, we are saying to shade above the boundary line. And on the other hand, if we have y is less than or y is less than or equal to, we're saying to shade below the boundary line. So in this example, we're asked to graph inequality y is greater than or equal to 2 times x minus 3 squared minus 5. So the first thing that we notice is that our inequality sign here has a equal to as well. So we can say automatically that the boundary line is solid. Boundary line is solid. We know that we're working with vertex form here. So our vertex is at 3, negative 5. So I'm going to go ahead and plot that down here. 3, negative 5 is my vertex. To find our x-intercepts, let's go ahead and just turn this into an equation. Y is equal to 2 times x minus 3 squared minus 5. And now we know that our x-intercepts are when y is equal to 0. So let's set this equal to 0, x minus 3 squared minus 5. We're going to add 5 to both sides. Then we're going to divide by 2 on both sides. Then we're going to square root both sides. So we'll have plus or minus the square root of 5 over 2 is equal to x minus 3. And now adding 3 to both sides, we'll have 3 plus or minus the square root of 5 over 2 is equal to x. So from here, we end up getting two x-intercepts, one where x is equal to 1.42, and we get another one where x is equal to 4.58. Really quickly, with our y-intercept, we know that's when x is equal to 0. So we'll have y is equal to 2 times 0 minus 3 squared minus 5. So we'll get y is equal to 13. So 0, 13 is our y-intercept. It would be somewhere up here. So probably somewhere up right over there. We have our two x-intercepts of 1.42 and 4.58. So 1.42 is probably right about here. And 4.58 is somewhere right about there. I know it's going to be really hard to be accurate, but we'll do our best. So like we said earlier, since our boundary line is solid, we're just going to quickly sketch our parabola. It's going to come down kind of like this. I'm trying to make as good of a parabola as I can. It's a little bit tougher than it looks, like I always say. And now we're going to determine algebraically if negative 3, 5 is a solution to the inequality. So this point right here, negative 3, 5, we know that it's going to be over here, negative 3, 5. Let's plot that just for some reference here. Is this a solution? So if we are looking at this and we're going to shade in this inequality, we're looking for every part or the region where our y values are going to be above that boundary line. So we can see here that if we were to shade this in, it's going to be everything that is in this region. So what this means is if we've done this properly, if we're proving this algebraically, will negative 3, 5 be part of the solution? No, it won't be, but we're going to verify that algebraically. So for us, we're going to plug in this value of x and y into our inequality. So we'll have 5 is greater than or equal to 2 times negative 3 minus 3 squared minus 5. And we'll have 5 is greater than or equal to 2 times negative 6 squared. That gives me 36 minus 5. So I'll have 5 is greater than or equal to, I'll have 72 minus 5. So 72 minus 5 gives me 67. So this means that this inequality is false. So therefore, I have to shade in the other region that this point is not contained within. So to answer this question here, we would say no, since negative 3, 5 does not satisfy the inequality, we must shade in the other region. So here in this next example, we're going to graph this inequality of y is less than negative 10x squared plus 35x minus 15 with our calculator. I've already gone ahead and plugged this function into there. I'm going to press enter. We'll draw this out. We'll see that we don't really see the top of our vertex there. Let's change our window settings. Let's change this to a standard window setting and let's see what we get. And obviously that's not going to work. Let's change this y maximum to, let's say 30 and see what we end up with. So we get something a little bit better. In order to figure out our key points, let's look for our vertex and our two x-intercepts along with our y-intercept. So we can see here that we have one at 0.5 and one at 3. So let's go ahead and sketch this out. So we'll have 0.5, we'll have 3 here. And then let's take a look at our vertex. So let's write down our x-intercepts, 0.50 and 30. We know that our vertex is going to pop up and we'll have a y-intercept somewhere. So going back to our graph, Let's look for the vertex. We're looking for a maximum, and we're at 1.75 and 15.625. So 1.75 and 15.75 and 15.625. And last but not least, we have our y-intercept. So we're going to g-solve and look for the y-intercept, and we have it at negative 15. So 0, negative 15 is where our y-intercept is going to be. Let's go ahead, let's put about 15 here. And we're going to sketch this with our intercepts. We know that because of this inequality sign, we're going to look at a dotted line. So our vertex is going to be right up just about here in the middle. We said it was at 1.75. So in the middle, right there, just above that 15, it's going to be a dotted line coming all the way down like that. And because we're looking for everything where y is less than this boundary line, we're just going to go ahead and shade in everything that's underneath the line, just like so. So in this inequality here, we're going to go back to vertex form and try to figure out the equation of our vertex given a few points on the line. So we can see here that our vertex is at negative 4, negative 6, so our p-value is negative 4, and q is equal to negative 6. Our point on the line that's given to us is going to be negative 6, negative 2. So we're going to go ahead and use that. So we have our vertex form. Y is equal to a times x minus p squared plus q. So again, the reason why we're using vertex form is we're trying to figure out what this boundary line is. So with our 2 points here, we'll have y is equal to, so we'll have negative 2 is equal to. We don't know what the a value is, so we're just going to leave that as a. Our x value is negative 6. Our p value was negative 4, so negative 6 minus a negative 4. And that's all going to be squared, plus q, so minus 6. So we have negative 2 is equal to, we'll have negative 6 plus 4, so that's negative 2. Negative 2 squared gives me 4a, and 4a minus 6. We'll add 6 to both sides, we'll get 4 is equal to 4a, and we'll get a is equal to 1. That means that our equation for our original parabola was simply x plus 4 squared minus 6. And because we're looking at an inequality here where it's a dotted line, we're just going to turn this equal sign into greater than. And it's going to be greater than because it's everything above the boundary line. So y is greater than x plus 4 squared minus 6. So here in this last real-life application problem, we have an arch that supports a bridge over a river. And it spans a horizontal distance of 250 meters and a max height of 125 meters. We're going to determine the quadratic function that models the parabolic arch of the bridge. So if we were to make a quick little sketch here, we would see that if we had everything underwater here, it's going to be everything under there. Our initial starting point of the bridge is going to be at 0, 0. We said that the end of the bridge is roughly at 250 and then 0. And then our vertex is going to be right there in the middle. We'll have this at 125, and we said a maximum height of 125 as well. So our bridge looks something just like this. And again, because we're not dealing with an inequality yet, I can just draw that with a solid line. And from here, we've got a couple different points we can choose to help us out. So we know that we have our vertex of 125, 125, and our point is going to be 0, 0. It's the easiest one to use. So looking at vertex form, we will have y is equal to a times x minus p squared plus q. 0 is equal to a times 0 minus 125 squared plus 125. So we'll have 0 is equal to a times negative 125 squared plus 125. Subtracting 125 from both sides gives me negative 125 is equal to 15,625a. And then isolating for a gives me a is equal to negative 1 over 125. So our quadratic function that actually models this will be y is equal to negative 1 over 125 x minus 125 squared plus, and maybe I'll move this over, plus 125. And if we're looking for the inequality that represents the space under the bridge, we're looking for all of this underneath. And we're not looking for anything that is on the bridge itself, so it's only under, so less than. We're really just converting this to y is less than -1 over 125, x minus 125 squared plus 125. And we can always confirm this with a test point to see if it is true or not. So this brings us to the end of the video. I know it was a bit of a long one, but if you have any questions or comments, feel free to leave them down below. As always, thanks again for watching, and I'll see you in the next video.